So pH is a way of representing solution acidity. And the definition of pH here is the negative log of the hydrogen ion concentration. So I'm just going to go through some stuff and then we'll explain a little more. There's a compact way to represent solution acidity. The pH is going to decrease as the hydrogen ion increases, and that's because there's negatives involved here. And there's just a little word about significant figures, because it's kind of a pet peeve of mine that so many, even chemistry teachers, don't understand what to do with significant figures and logarithms. So the number of decimal places in the log is equal to the number of significant figures in the original number. And so we'll do some examples and figure that out. You've probably heard of pH. Commercials for shampoo always talk about pH for some reason. And if you own a swimming pool, you know, you have to keep the pH within a certain range or it gets nasty. So a pH of 7 is considered neutral. If the pH is greater than 7, it's considered a basic solution. If the pH is less than 7, it's considered an acidic solution. And the lower it is, the more acidic it is. So pH 7 is neutral, above is basic, below is acidic. So here's a nice illustration of the pH scale. So let's look at hydrogen ion concentration first. So we just learned about this little relationship. Let's get the readable color here. That the hydrogen ion concentration times the hydroxide ion concentration always equals 1.0 times 10 to the minus 14. Right, we learned that before. So if we have an acidic solution, that means we have more hydrogen ion than hydroxide ion. And so the left column on this giant arrow shows the hydrogen ion concentration. And as it's going down here, the hydrogen ion concentration is increasing. So here the concentration is 10 to the minus 1, and up here it's 10 to the minus 13. 10 to the minus 13 is smaller. So when the hydrogen ion concentration is larger, this is more acidic. That makes sense, right? These numbers, because the hydrogen ion concentration in water can vary from about 1 mole per liter, down to 10 to the minus 14 moles per liter. That is a huge range, 14 orders of magnitude. If you try to graph that, it doesn't work out very well, because everything ends up being all bunched together at the end, because you've just got this huge order of magnitude change. And so what we do is we use a logarithm to linearize and compress this into something a little more manageable. Now if you look at this, there's a pattern here. 10 to the minus 14, the pH is 14. 10 to the minus 11, concentration, the pH is 11. 10 to the minus 10, the pH is 10. Do you see the pattern there? The pH is that exponent made into a positive number. That's what this equation does. pH equals the negative log of the hydrogen ion concentration. Negative log is not anti-log. It's you take the log of the hydrogen ion concentration and you change the sign. It's just a negative sign. If you take the logarithm of 10 to the 4, the log of that is 4. Because the logarithm says what power of 10 is this number? And if we're dealing with, nice things like 1 times 10 to the 4, then the exponent is the log. And when it's a small number, like 10 to the minus 3, then the log of that would be minus 3. For the pH, we say, well, we don't want to mess around with all these negative numbers. We're going to change that And so the pH, so this is taking the log, that first step, and this is changing the sign. So the pH of a solution that is 10 to the minus 3 molar in hydrogen ion concentration is 3. So logs are kind of mysterious things, and yet if you just look at the factors of 10, it's not that crazy. You have a question?
Where did you get 10 to the 4?
I made it up.
It's still 4.
Well, the log of 10 to the 4 is 4. If I took the pH of something that was 10 to the 4, then it would end up being minus 4, but that's not actually possible. So you need to know how to do this on your calculator. Before we get to that, let's just talk about, so get your calculator out while I'm talking some more. So what this does is it changes this range that spans 14 orders of magnitude, and it makes it into a nice range from 0 to 14. So it just makes it much more convenient to deal with. Over here, it's listing the pHs of some common substances. So 1 molar sodium hydroxide, that's not exactly a common substance, but you might find something like that in drain cleaner. Household ammonia is going to have a pH around 12, so that's a rather basic solution. Right here in the middle, you've got pure water at 7, and you've got milk and blood. It's going to be very close to pH 7. The pH of your blood is 7.4 plus or minus about 0.1. Yeah. And your body regulates the pH of your blood very tightly. Because if the pH goes too high or too low, you die. Because all the chemical reactions that are occurring in your body are dependent on the pH. And if the pH is off, then some of those reactions are going to go too fast or too slow or not at all, and just it's really, really bad. And so your body has all these different ways of controlling the pH of your blood. It's pretty cool. It really is. And so if you get into like biochemistry or biological chemistry, then you learn a lot about that and how your body does that. It's all chemical reactions. So down here, vinegar, lemon juice, stomach acid. Okay, so these things are quite acidic. Sometimes people say, well, you shouldn't drink soda because it's got phosphoric acid in it. Yeah, well, maybe you shouldn't have a stomach because it's full of hydrochloric acid. 1 molar hydrochloric acid is a pH of 0. Your stomach acid is here around 2. Your stomach acid is very acidic. Like, well, why do we need antacids? Well, sometimes your body gets a little out of whack, and your body makes too much stomach acid, and then you have heartburn or acid reflux disease or something like that. And then you put things in, you take medicine to help either neutralize the stomach acid or to convince your body to quit making so much.
Yeah, that happens to cows and they blow up on the inside.
Nice.
Or kill.
Yeah.
And you stab them.
And let the gas out. Yeah.
And the steam. You hear it.
I've heard of that.
They'll
I've
die
actually.
if you don't do
Well,
something.
yeah. So it's better than dying.
With a needle, like
Yeah, you don't stab them with a knife or something.
Like in an emergency, though,
You
if you
can stand
can.
with a stiletto.
Back in the day, guys used to be like, you had to, it was life or death. You
Well-
stab them with a screwdriver or something, and they would deflate.
Because otherwise they'll blow up,
Yeah,
basically.
blow up.
So all you YouTube
And it
people out there,
smells worse.
you see a cow that's big old swollen on one side, take a screwdriver and stab them and let the gas out. No, call the vet, yeah.
I mean, they'll just die. I don't know why they die.
What do you think?
Okay, so let's learn how to calculate pHs. So you got your calculator out, right? I told you way long time ago at the beginning of the semester, you need a calculator that's got a log button on it. So it should have an LOG button. We're going to use that now. So some of your calculators you need to put the number in first and then press the log button. Other calculators you need to press the log button first and then put the number in. So you have to figure that out. So how would we calculate the pH for these two solutions here? Well, the first one's going to be simpler than the second one. Calculate the pH. We have to remember, what does pH mean? pH is negative log of the hydrogen ion concentration. So we need to know what the hydrogen ion concentration. For letter A, they gave it to us. And so here the pH is equal to negative log of 1.0 times 10 to the minus 4. So on your calculator, I should get my calculator out, you would press 1 EE minus 4, press the log button, that should give you minus 4, should give you minus 4, and then you press the negative, the change sign button, and you'll end up with 4. Okay? Now let's just, I'm not going to trick you with sig figs on an exam, but let's just practice doing them. 1.0 times 10 to the minus 4, how many significant figures does that number have? It has 2. So in the pH, the significant figures are only after the decimal point. And so we really should write this as 4.00. So the pH is 4.00. Right. And I'll show you why in a minute. Because the 4 is the exponent. 10 to the minus 4, that's where that 4 comes from. So the digits to the left of the decimal point in a pH value refer to the place holding, and so they're not considered significant figures. Well, I'll do some extra examples. So 4.
Do you round this number?
Well, you just count the number of significant figures. The rounding would end up being the same. Yeah. So any questions about that one? So letter B, 0.040 molar hydroxide ion. Does that fit into the pH equation?
Yeah.
No. It's not the hydrogen ion concentration. It's the hydroxide ion concentration, right? So we have to figure out what the hydrogen ion concentration is. So remember that it was H plus times OH minus equals 1 times 10 to the minus 14. So we've got the hydroxide ion concentration here. We're solving for the hydrogen ion concentration. So we're going to divide by the OH minus on both sides. These guys cancel out over here. So the hydrogen ion concentration is 1 times 10 to the minus 14 divided by 0.040. And you can treat that 1 times 10 to the minus 14 like an exact number. So 1 EE14 negative divided by 0.04. 2.5 times 10 to the minus 13. And that is the hydrogen ion concentration. That's what we need to find the pH. So the pH equals negative log 2.5 times 10 to the minus 13, which will be 12 something. 12.60. pH doesn't have a unit. It's a unitless quantity. Chaos. Pure chaos. Well, do you want to deal with logs of units? I don't think so. We always do the molarity, the concentration in moles per liter, molarity, and then we take the log. So 2.5 times 10 to the minus 13 has two significant figures, and so that's why I wrote 2 decimal places. Anybody need me to talk to their calculator? You getting it to cooperate? You want me to come talk to your calculator? Yes, okay.
How'd you go with the same things?
Okay, so let's look at what happens with the significant figures, because I think it's kind of interesting.
So say you
I thought it said something
three
about
decimals
decimal
in the original
places.
number, would you put 3 decimal places after?
Yeah, if there were 3 digits in the original number, then you would put.
So this would be 6.02 or 0.602.
Just a minute. Having an issue. What was your question?
So if you had like 3 safe things, say it was like 2.50.
If it was 2.50 times 10 to the minus 13, then it would be 12.600. So I'm going to leave this guy down there. It'll probably be easier just to write that over than erase all this, but I feel like erasing it because it's kind of fun.
Kind of fun.
It is.
It's like you're uncolored.
Yeah. It's like, I wish I could erase the dirt in my house that fast. So down there, the 2.5 times 10 to the minus 13 ended up being 12.60. What if we do, what if we find, put a pen on there now. What if the hydrogen ion concentration was 2.5 times 10 to the minus 3? What's the pH?
$2.66.
2.60. If the hydrogen ion concentration is 2.5 times 10 to the minus 7, pH is 6.60. Right? Check me on that. I did that in my head.
You did it in your head.
I did it in my head.
Because you memorized it or you did it in your head?
I did it in my head.
You're a genius?
I'm not a genius.
That sounds pretty genius to me.
So 2.5 times 10 to the minus 10th molar is 9.60. Did that in my head too. It's a pattern! Yes!
I have so much faith in you.
You have too much faith in me. There's a pattern here, isn't there? What's the pattern?
Sixes and zeros.
If we have 2.5, those are the significant figures, right? Then we end up with 0.60. The only thing that's changing is the part in front, which is 1 less than this exponent. So the numbers before the decimal point, and if it was, if it was 2.5 times 10 to the minus 14, then it would be 13.60. Doesn't matter how many of them there are, but these numbers are not significant figures. They're place-holding zeros, essentially, because they come from this exponent. We don't consider those exponents to be significant figures. They just tell us where the decimal point is. And so the numbers before the decimal point in a pH are not considered significant digits. Okay? That's not that hard to understand, is it? When you line them up like this and you see, the only thing that's changing is that first number. And so this part is reflected in that part.
So the only part that you're not showing up here is like the fact that you put negative before the log in your calculator.
Say that again?
Like you're putting negative along with the log log in the calculator, but you're not showing it there, right?
What I do is I take the log and then I change the sign.
Okay, gotcha.
And what I was doing by doing these in my head is I realized that it's going to be one less than the exponent, and then the decimal portion is the same every time. So that's just kind of a trick.
Our answer for pH will always end in 0.60.
No. If it's 2.5 times 10 to the something, it'll be 0.60. Otherwise, it'll be something else.
3.2 to 10.
So,
Will the power to 10 always be one
hey,
less?
but I still don't see it.
Yeah.
Okay.
Yeah, thrown off somewhere along the line. So it's 12.60 because 12 isn't counted for the
Because we don't count 12 as the sig figs, yeah.
for pH. So
For pH. It's because of that logarithm.
it's 2 sig figs because 2.5 is 2 sig figs.
Yeah. And I want to show this to you, but I'm not going to test you on it. I'm not going to, give you multiple answers, and the only difference is that some of them have the wrong number of significant figures. So hopefully I just think it's cool. Okay. Seems like I'm missing a slide here, but maybe not. The pH of a solution is a 5.85. What's the hydrogen ion concentration? So, what do we know? We know the equation for pH. So, pH equals negative log of the hydrogen ion concentration. But now we know the pH and we want to know the hydrogen ion concentration. Rearranging this equation is a little more complicated. I'm going to show you how it's done, but then I'll give you both forms in the cheat sheet. So the first thing I'm going to do is I'm going to multiply both sides by a -1. So that makes this side positive and that side negative. And then I need to get rid of log. Log is a function. You can't just divide by log. It's a function. You have to do the anti-function to get rid of it. The anti-log is 10 to the x. And so I take 10 to the power of each side. And the 10 to the power and the log cancel each other out, and that equals the h plus. That is probably a math thing that you repressed or erased from your brain long ago. Okay, so I don't expect you to remember that. But for those of you who are a little more fond of math, or just a little curious, and how do you do that? Why can you do that? That's why you can do that. Here's the bottom line now. There's the equation. If you have the pH and you want to know the hydrogen ion concentration, use this equation. So here we're trying to find the pH of a solution, the hydrogen ion concentration when the pH is 5.85. So the hydrogen ion concentration equals 10 raised to the minus 5.85 power. And don't tell me you can't do that, because you can. So on the same button as your log button should be a 10 to the x button. That's what you're going to use. And again, on some of your calculators you have to put in minus 5.85 first and then press 10 to the x. And on others you have to press 10 to the x first. On my TI-30XA I do the number first. So 5.85, and I'm going to change the sign to make it negative. My 10 to the x is the second function, so I press the yellow second button and 10 to the x, and I get this number with a whole bunch of zeros. And kind of a rule of thumb is if you can't tell immediately by looking at a number how many zeros there are, put it in scientific notation. If you can look at it and see, oh, there's 2 zeros, then fine, write it that way. So I'm going to put that in scientific notation. And how many significant figures should I write down? 0.82. It's the 0.85 that comes from the coefficient in this number. So I'm going to write 1.4 times 10 to the minus 6. So that's the hydrogen ion concentration. Make sure that you can convince your calculator to give you that number. It's not exactly a slam dunk all the time.